went through some of the examples, including the arithmetic and also the branch instruction and the memory instruction. Right? There are other types of instructions that the ISA needs to support. And we mentioned this before. Like for example, what if you have an immediate value in your operation? How you handle it, right? And as you can tell from the discussions we are having, we are not simply enumerating things. We're just trying to think as if we are those that make the decision, right? So what the options that we have, what decisions they make, what are the trade-offs, why this option is better in this case, why this one is better in that case, right? Because after 5-10 years, you might really forget all these kind of details. But hopefully the reasoning is the important part, right? If you understand the reasoning and you are able to replicate it in your own engineering life, it's in fact one of the most important things in any course you take, right? So again, the style will be doing stuff we have been doing so far. Hopefully you have already noticed that. You are trying to reason about the decision. If there's someone that is designing an ISA, what decisions they are making, why they are making it, what are the possible options they have, what are the trade-offs, right? Good. And generally in computer architecture, there is rarely one solution that works for everything. There is no one size fits all, right? All the time you have to make compromises. You make a decision in favor of one thing, or paying a cost in another thing, right? And this is not only in computer architecture, that's a general engineering concept, right? Okay, so we will go back to the instruction types. We said you need immediate values because most of, if you look into any C programming I've written before, any Python program, you have arithmetic operations that operate on variable registers, but you also have constants in your code, right? You say, for example, well, in a for loop, you are always adding I equal I plus 1. You increase your counter by a constant value. That's right. There are multiple options on how to deal with this constant value. One of them would be, well, I just deal with the constants as they are memory locations. I'm going to store them in my memory, and then when I need them, I load them, right? You transform your constant into a memory location. You store the value there, and then you access it from the memory. What is the disadvantage of that? Very slow, right? Every time you have a constant, go bring it from the memory. We said memory is too slow, right? You don't want to do that. What other options? Well, I have special registers for the constants, right? As you might imagine, constants are literally infinite, right? So if you have 32-bit machine, you have 2 to the power 32 constants, right? So you cannot have 2 to the power 32 registers. That's almost impossible, right? So if you want to dedicate a register that says, okay, I'm going to store this value. For example, I have a register that stores the value of 0, a register that stores the value of 1, and then 2, and then 3, and then 4, such that when I need it, I can access that register. Doesn't make any sense, right? But there is the observation that there are constants that are more commonly used than others, right? For example, you have to deal many times with the 0 constant, right? Then 0 has very special characteristic when it comes to arithmetic operation. For example, multiplication by 0, you don't need to do the multiplication at all, right? Addition to 0, you don't need to do the addition at all. Subtraction, the same thing. So a 0 value can be handled as a corner easy case in most of the arithmetic operations, correct? And for this purpose, well, it might make sense you dedicate a register that you hardwire to 0, right? And this is what we said yesterday, that we have a 0 constant in the MIPS ISA, right? What else you can dedicate at the register? Maybe 1, right? If we are incrementing, we always have a counter by 1, then I can have a register that is dedicated to 1, right? But then if you add another 1 to 2, or 3 and then 4 again, you start losing the area because you cannot really add as many registers as constant are there. So the general concept of adding a register bare constant doesn't work. Might work for some very common cases like a 0, maybe a 1, some ISAs, but it will not work for others, right? So we still need to find another way to handle constants. We said memory doesn't work. It works functionally, but not very effective. Register is also not a feasible solution. What can we do else? Well, I basically have a special instruction that contains the constants inside them. And this is not a new thing. We looked yesterday into branches, and we found that conditional branches, especially, you have a condition, you read two registers, you resolve the condition, but then if the condition is true, what you do? You jump to a certain address. From where you obtain that address? The instruction itself, right? We said we are storing, if I go back, where we had the conditional branches, here, for example, so this is the conditional branch format. We had a 16-bit offset where we can store our address, and we had this detailed discussion about, well, if we want to jump further, what can we do? What are the limitations? But then you store your constant address as an immediate value inside the instruction itself. So this concept of storing values inside the instruction format, we have already seen this, right? So if we want to generalize this for immediate values, we can simply say, okay, I'm going to include any immediate value that I have in my arithmetic operation, for example, inside the instruction. I'm going to have a special instruction that is called add I, for example, which is simply adding, and it includes an immediate value. I is for immediate. And then, for example, here I'm adding the stack pointer plus 4. Or any other special register or general register, that doesn't really matter. Then, well, the same thing for shift left with a constant value, or shift right with a constant value. Or, well, SXI in maps is not in fact a shift, it's set if less than immediate. You are simply comparing S2 to 15, less than, then you set T0. So it's a very special instruction in maps. It's called set if less than, right? And we will come into that instruction later on. We use it in some interesting stuff. But the general format is pretty much similar to the conditional branch ones, right? Again, I have an offset. Right now, I don't call this an offset because it's not an address, right? It's a general immediate value, it can be anything. And then I also have, well, a source register and a destination register. If you compare this to the normal arithmetic stuff, what did we do? What did we change in the format? In the normal arithmetic add, for example, we needed two sources, one destination, right? But here, because you are using your immediate value as one constant, you are spending 16-bit for it, and you only need one other operand as an input. So, for example, if I'm adding this register with this register, so I need SP to be my first source, 4 is my immediate value, and then I add both, and then put the result in the distribution SP as well. Good. So you need one source register, one destination register, and your immediate value. Sense? So why we need to care about immediate value instructions? Like, for example, why I don't really put this in load it in a register and then add a register? Because it's very common in our application. So as we said at the very beginning, another important concept in computer architecture is to make the common case fast. So if there is something that keeps repeating again and again, it's better to optimize, right? If you do the same task in your daily life every day, maybe you better do in an efficient way, because otherwise it will waste you a lot of time, correct? So here, immediate instructions or immediate operations, arithmetic operations are very common, right? And we have already seen the example of this related to the memory operation. Remember, in the memory load or store, the format was that you have a destination register for the load, for example, but to compute your address, we needed an address that is stored in the register, and then there is an offset, right? For example, we said 4 and then R4. Then we said you add the constant to the register value to obtain the address. We needed an add operation. In fact, it's an immediate add operation, right? So it's very common in address resolving. It's common in loops, for example, because you have stride values or you have a constant increment, right? It's also important for initialization, especially zeros. You handle them very frequently. This is why you dedicate one format, one instruction format for them. Good. And the constant is kept inside the instruction itself, as I've said, but then you are limited again. This is the same limitation we had in the conditional branches, is you are limited to certain constant value. The question is, what do I do if I need to add, for example, more than 2 to the power 15 minus 1? Right? Something that spills over this length. Can you suggest a solution? If I want to add a value here, for example, that is not 4, but rather a very, very big number that exceeds the 16 bits, what can I do? Very easy solution. Yeah.
What can you do like the instruction on the
Exactly. Thank you. So simply, well, you can divide this number. If you want to replicate it twice, if I'm adding, let's say, I don't know, 4 million doesn't fit here. So I'm going to add 2 million first, and then another 2 million, right? So you basically repeat that instruction, right? And then you add it twice to fit. The general solution for this is you simply can also divide your value into 2 separate parts. What I mean by this, our registers are 52 bits. If I want to add a value into them, to this 32 bits, I can say, okay, I'm going to divide my value into an upper half and a lower half. And then I add the lower half to the lower half of the register and the upper half to the upper half of the register, right? But then because you need your value to be shifted so that it goes to the upper half, you need to use a special instruction that's called load upper immediate. What does it mean? I'm able to load a constant value, but I'm going to load it to the upper half of the register. Again, our register is 32 bits. You can divide them into 16 lower and 16 up, right? And then I have special instructions that enables me to load immediate values to either the lower half or to the upper half. Sense? Why this might be related to the discussion we're having right now? Because I can add bigger constants or multiply them or do any operation with them by understanding that I can manipulate the 2 halves of the register separated. We said our immediate value is 16 bit, correct? Which in fact matches the width of half of the register, right? So if I want to add or multiply a constant that is bigger than 16 bit, I can divide it into, let's say 52 bit, for example. I can divide it into 16 and 16. 16 that would operate with the lower half of the register, and the upper 16 would operate with the upper half of the register, right? So you divided your operation, well, into 2 halves to do for the lower half of the register and the upper half. Make sense or confusing? Okay. And then, well, this is because now you have 2 halves, 2 different bits, 0 to 15 and then 16 to 31. What if at the end of the operation, I need to combine them into the one register, right? But we're using the symbol OR operation to do that, right? Because here, for example, let's say I want, well, first of all, I'm loading this, the upper half of the register. So assume this is originally my register, and then I'm loading this value into this upper half, right? And then assume this is the other half of the constant that I want to add, and I want to put at the lower half. If I also do the load lower half, it will come here, but this part will be 0, right? So now you ended up with 2 registers. One has a value in the upper half, but the lower half is 0. And another one that would have a lower half value, but the upper half is 0. If you want basically the 2 values, what you do, you OR them, right? Because simply these are 0. If you want this value and this value in the upper and the lower, if you do a simple OR operation, or simply done. Okay, are we good so far? So what we discussed so far is this type of registers and this type of instruction. We said we simply have our memory, which is quite addressable. Memories can be, well, we're loading stuff from the memory as like a word, which is 2 bit or 4 bytes. And then we have a register file that we call this part of the data bus. We said in MIPS we have 32 registers, which means we have 5 bits as addresses. So we have 2 read ports, 1 write port. That's why you can have 2 sources, 1 destination at a time. This is simply the data that you want to write. You are writing to the register. This is the read port. So this is the read data. It's 32 bit. The write data is 32 bit. These are the addresses that you can have, both for the source register and for the destination. And then we said, well, for the branches, what I'm trying to show you here right now is how, in fact, those instructions, the fields that we discussed yesterday, can get materialized into hardware. What is the simple logic that we can do them? We needed the register file, we need the memory, this is the data path. With regard to the control path, well, we said there are three main operations we are doing in our processor. We're fetching the instruction from the memory, decode it to understand what it really means, and create the selection signals and the control signals, and then feed this to the data path to execute, right? Later on, when we come to the pipelining, we know that we can break down these steps into further, right? And also in lab 2, you will see that Maxim has 5 stages and only 3, right? So you have fetch, decode, execute, but you can have a memory stage and you can have a write back stage, right? So we'll discuss this later on. But then for the simple arithmetic and shift logic operations, you have an ALU that most probably you have designed in the digital design course, right? You have an adder, subtractor, shift operations, right? The ALU accepts 2 operands as an input and gives you 1 destination out, right? These 2 operands can be either 2 registers, similar to the arithmetic operations we discussed yesterday, or 1 operand register and 1, what would be the other option? Immediate value that we're discussing today, right? We can have 1 immediate, 1 register or 2 registers, and then at the end you have to write 2 values, right? So this is for arithmetic and logic operations. For the control flow instructions, the branches, then we said, okay, I have, the branch is called control flow because it controls the flow of the program by manipulating the program counter, right? This is why here you find the program counter laying a rule into the branch. Right? What happens is that traditionally, if you don't have any branch at all, you have your program counter and you add it by 4, right? Why do we add it by 4? To get the subsequent instruction to execute. All our instructions are 52 bits, right? But then if you ended up having a branch and this branch is taken, which means you need to jump, in that case, instead of adding the 4, you in fact need to add also the label, the offset that you need to jump to. From where do I get that offset? How to obtain that value? From the instruction itself, like we just said this 5 minutes ago, right? That branch, a conditional branch, already have a 16-bit offset that we simply can add to the program counter to jump to the new items, right? And we had already did discussion that what if I want to jump to a further place? This is not enough. Then I translate this into an absolute jump, right? And then I basically have a 24-bit instance. Good. You see, this is basically how the hardware is really implemented to execute this instruction. Right now, we have them completely separate, like distinct, but they're all connected, but I don't want to complicate stuff. Hopefully later in today's lecture or on Friday, we're going to put it all together, how the data path and the control path looks like in a real process, right? But now we're looking into separate instructions and what pieces of hardware, what modules we need to execute them. Questions? Make sense? If you are designing a processor, in fact, you start building these modules first, then you connect them, right? You start building everything in a standalone, maybe even create a test bench for it, test that it's working as intended for the branches, for example, and then you integrate everything together. Good. Okay. Yeah, and here, well, we discussed the arithmetic operations, the control flow ones, and the logic ones as well. And we also discussed the memory operations, right? The memory deals with the memory, that's why there is the interface between the processor and the memory. So you have load and store, and there are load word, store word, load byte, store byte. Usually you go to the memory, it's a 32-bit because you register the 32-bit, so the address is 32-bit. And you have the read or write address. If it's a load, that means you need to get something from the memory, so you receive a data through the read data path. This is 32-bit. Or if you are storing, then you are writing something to the memory to a 32-bit. Right? Here is shown that the read and the write are separate buses. It depends on your implementation. For example, we will see in the cache lecture, fact a separate wire for the load and the store. So you can do a load and store in parallel, but for the main memory, it's in fact a unified bus. You can either do a load or a store at a time. So this is the summary that we discussed. Again, we have arithmetic operations. They can be immediate or register formats. We have data transfer, load and stores, whether we are word or byte. And we also have load upper immediate. Right? The upper and lower, we already discussed this philosophy that you can load something to the upper 16-bit or the lower ones. By the way, Intel had a way via divergence from what you are saying that even in early 32-bit machines, they had a way to be able to combine 2 registers together to form a 64-bit operation. For example, if you wanted to add 64 bits, you will be using two registers together and use them as lower and upper. It was a very complicated way, right? And also eats up a lot of registers. Instead of having two operands right now, you need four registers. Right? But this was an Intel thing to enable high performance without increasing the machine width, right? The register width, most of the time, people in computer architecture or computer organization refer to it as the machine width, right? Because as I was saying, this dictates everything. Your register width dictates your address width, dictates how many memory you can have maximum, everything. So if you hear the word machine width or you read it in a data sheet, that means the width of the registers in your register file are either 8-bit, 32, 16. Okay, so here we're going back to something that we call the addressing node. And we already discussed it, but just to make sure you guys are familiar with the terminology itself. Simply, I can have what I call register addressing. And register addressing here means your operand is in fact a register, right? Again, mainly these are the R format instructions, like the add, subtract, that have two open registers. You can also have what we call a base addressing or displacement. An example for this is the conditional branches, where you have an offset that simply get added to a base register. In case of our branch, what is our base register for the branches? Idea? So I'm having an offset in my branch. I call it displacement or offset because I add it to something. Yeah.
The program counter.
The program counter. Thank you. Right. So you just had this circuitry right now, right? Right here. You said the program counter get added to the offset to give you the absolute address, right? That's why this is called an offset or displacement, because it gets added to a base address, right? In the branches, it's the program counter. And this is why it's called the relative addressing, because again, you add an offset to something else. And then you have also an immediate addressing, where your operand is simply an immediate constant. And we had the add-I instruction, the sub-I instruction, where one of the operands is immediate. Okay. So this thing here, this base displacement, is simply a special case of it is the program counter relative displacement, as we were saying in the instruction, in the conditional branch instruction. And then we have something that is simply, we called it yesterday a direct jump. Right? But in fact, it's not fully direct, because if you remember the jump format, we said this width of the jump address is 24 bits, right? It cannot be 32, right? Your width of the whole instruction is 32. But you in fact need 32 bits for an absolute address, because your memory is 32-bit addressing, right? That means you cannot use this address as is. What you do instead is you simply do some sort of a math operation between this one and the program counter to get the absolute address. This math operation, as written here, simply instruction addresses 26 bits in that example. In some other ICs, 24. I kept saying 24 multiple times. Here in bits, it seems 26. And then you concatenate this with the other 4 bits of the program counter. So simply, if this is 26 bits, I need 32 bits to jump, because otherwise I don't have an absolute address. So you take this address as is. How many bits are left after 26? You need, in fact, 6 bits, right? You concatenate 6 bits. Why this is 4? Well, this is a good question. So why I'm only concatenating 4 here? Well, this might be a bonus question. But it's a hard question. The output takes. Yeah, well, the output of the instruction itself, right? But here we're calculating the original address, right? So simply going back, what is the steps? I need a 32-bit address. I only have 24 bits, right? Makes sense? So you take the 24 bits and you need to find the 6 bits from somewhere else. What we're saying here is you can concatenate the 4 bits of the most significant of the program count. But this gives you 4 plus 26, 30. There are 2 bits remaining. Yep. Thank you so much. Yeah, great. Yeah. Wow, that's great. I'm happy that someone managed to get it. So the idea is the following. Where are we using, this is a jump instruction, right? So the semantic of the instruction itself tells us what operations we are dealing with, right? If this was, for example, a normal load or store, you can deal with any way, right, of data. But jump deals only with instructions, correct? But you jump to a certain program counter value. So there you obtain an instruction. And we know that all our instructions are fixed at 32 bits, right? Which means there are 4 bytes, correct? So you, in fact, jump in the granularity of 4 bytes at a time. For 4 bytes, how many offset bits you need? How many bits within the 4 bytes? You need 2 bits, right? If you look in an absolute address, you will never find an instruction address that is like this, for example. 0xff something, and then 31. It will never end like that, right? Why? Because there is no alignment for this address. To be able to address instructions all of the time, your most significant, this cannot be 1. Your most significant bits, him talking about bits, must be zeros, right? Your most significant least significant 2 bits. Why? Because all my instructions in the memory are in the granularity of 4 bytes each, right? So I have one instruction here. The next one is after 4 bytes. And then the next one is after 4 bytes. So if my first instruction is starting at address 0, the next one is at address 4, right? And then 8. So by default, if you look into this address, this is 00, this is 001, this is 001, right? Etc. etc. Right? So in that case, all the time, your first 2 bits are in fact zeros, right? Make sense? So this is why you already know them. You don't need to store them or calculate them somewhere. What you really do here, you take the 24 bits, concatenate the most significant 4 bits of the program counter, and add 00 at the first 2. Because your instructions are aligned, 4 byte aligned, right? Make sense? Okay. And this is why we call it pseudo direct. But it's not really absolute direct because you don't have the full 32 bits at hand. You really need to calculate it. But still direct because you don't, for example, do an offset displacement like the conditional branch. You still have an absolute address that you just simply massage a little bit to obtain the full address. Okay, so some of the principles, again, to revisit them to conclude that topic. And this is not only maps a general risk, fixed size instructions to simplify stuff. Here we're saying simplicity favors regularity. Why regularity is very important? Because if you have a very regular behavior, you can optimize your hardware to accelerate the operation of this regular behavior, right? So you have fixed width instructions. You have small number of instruction formats. We said earlier when we started this topic is smaller number of formats you have, the easier for the decode unit to basically differentiate between them, right? So the logic is easier. Yeah, so take this fixed size as an example. We said in RISC, all our instructions are 32 bits. A very typical regular behavior is add your program counter plus 4 after equal, right? We talk about Intel x86 or CESC, instruction widths are not fixed. Every time you need to figure out what value to add to the program counter. It's no longer good. Okay? And then a small number of instruction formats. Compare those 4 formats we discussed. So if you open an Intel or x86 data sheet, see how many formats they have there. So I remember when I was in my undergrad, we in fact studied x86 as an example of ISA. There was like around 50 pages only to go through the formats. There are so many formats. Every format has a complication of how you add things up and the width and how this can be variable, how to figure this out. So someone that is really has a very, very complex, or smart definitely, but very, very complex mind to be able to come with all these things together, which complicates the hardware a lot. Then opcode is always the first 6 bits. If you observe something in all the formats we discussed, it's all the time here. We start with the opcode. Why this is something good? Why do you think this is something good? simplify, for example, the hardware.
Decode unit or
Exactly, thank you. If I'm writing a decode unit hardware and I need to extract the bits to understand what instruction it is, you know always that you can basically wire the most significant 6 bits, for example, to be able to decode what the instruction is. And based on this, you know where to find the remaining fields, right? So this is like something as a header. You start by it to be able to understand what happens in the remaining fields. Right? If it was in different places, well, it becomes way more common. But Cisco also defined the fixed place for them. Otherwise, it would be very hard to figure it out. And then again, we said everything would have a compromise. You have 3 instruction formats. Smaller is faster, but you have a limited instruction set that does not do everything. You have limited number of registers in the register file because you only have 32 and you have the integer. Later on, there are RISC ISAs that also added another 32 registers for the floating point. We have an integer register file and a floating point register file to increase the number of registers. Then definitely later on, they added the 64-bit support, right? A limited number of addressing modes. This is no longer a limitation because everyone simply is trying to do that. Again, when we say limited compared to the Cisco, where any instruction can in fact have memory direct address to perform the operation on, right? We never mentioned here that part of your operand is in fact a direct memory location, other than for the load and the store, right? But if we talk about the example we gave earlier about x86, an add instruction can have all the 3 operands as memory addresses. And then the main principle that's coming from Amdahl's law, make the common case fast. Arithmetic operands are simply very, very common. Then all the time you want to operate from the register file. Allow instructions to contain immediate operands as we discussed today, because they are also common in figuring out addresses. They are common in dealing with branches. And in that case, you want simply to embed the immediate value inside the instruction format itself, instead of storing it in the memory or storing it in the register file. Sense? So this is basically summarizing all the trade-offs we have discussed in the past 2.5 minutes. Questions? Okay. So here you'll find in the rest of the slides some kind of revisions. I will step through them. This is the number representation. Again, it's a digital design 3DI topic. I think here, make sure you guys understand it. Least significant versus most significant. How you have less than 32-bit. If you want to extend them to 32-bit, we have what we call sign extend or zero extend. You call these topics. You have a small value, an 8-bit number, and you want to represent it in 32 bits. Well, you can extend the rest with zeros, or extend the rest with the sign. You see, did you call when we need to do both? If the number was unsigned, then extending with zero is safe. But if the number was signed and you extend with zero, what's going to happen? If the last bit was a representation of the sign, but then you did a zero extension, you lost the sign because the last bit will become zero right now. So it's no longer a negative bit, right? So that's why we have what we call sign extension, right? You take the last bit and replicate it. Well, this is the ALU that we had in the previous figure. We take 2 operands as an input. Here, these are the flags. Simply the result is either zero, overflow. This is the selection logic. What kind of operation you want to do? Do I want to add, subtract, multiply, do a shift? Then you output the result to the destination. And these are some of the example instructions that simply can support your operation. Well, why do I have be equal, like the branch, the conditional branch, as part of the ALU needed for support? This is a control flow instruction. It's not an arithmetic operation. Yeah, exactly. Thank you. That's I need to basically figure out the condition of the branch because it's a conditional branch, right? So BE equal, this is branch if equal, branch if not equal. So in the set if less than immediate, and unsigned, and then the U extension for the RISC in general is referring to unsigned operation. Okay? And then I also need to support the logic operations, NOR, OR, I, store, and the I, as we know today, is the immediate value, right? And you also need to support the usual arithmetic operations, addition, subtraction, multiplication, and again, signed and unsigned. Two's complement is another topic. Again, I would not revisit, but it's very, very important. I mean, if you don't understand two's complement by now, I would say I would sit for a day and understand it, right? You cannot really graduate from that department without knowing what is, or any other department in engineering without knowing what is two's complement, right? It's something very important to understand. And then how the ALU is composed of one bit full adder, and then you concatenate them to create different types of adders. There's the Raven carry adder, there's the carry forward adder. There are multiple types of adders that's usually either covered in digital design or arithmetic courses. We don't need much of this right now because this is a lower level computer organization. But what we need to understand is behind this block that's called the ALU, it's composed of sub blocks. If you remember lecture 0, assembly, multiple multiplexers, gates that compose circuitry, and at the end it will go to the transistor. Again, it's another digital design discussion for the addition. If you have an overflow, what overflow? This was related to one of the questions that your friend here asked. Overflow in addition generally means when you add two numbers. Let's say, for example, I add two 8-bit numbers. What do you expect the result to be maximum? How many bits? If my two operands are 8 bits, the result would be for the addition. How many bits? 9 bits, right? Why that's the case? With 8 bits, if all ones, just the maximum value, if you add 4, you simply multiply by 2 if you add 1 extra, right? The 16 is for the multiplication, right? To get to the power. These are also things that you need simply to get in top of your head. You get naturally, right? You don't need to think about them, right? So if I have 9-bit as an output, we have a problem right now. My registers are all 32 bits. My two operands are 32 bits. My result is 32 bits. But I'm expecting the result to be 33, worst case, maximum. What do I do? You cannot have 33 registers, like 33 bit registers. What you do is you add a bit that's called overflow bit, right? So the overflow bit is simply detecting whether your result exceeds the maximum width of the machine or not. How to determine this? Simply look into the last bit value. If you have a carry out of the 32 bit, right? That means this carry will go for the 33. That means you have an overflow, right? So the simple circuitry for the overflow is to take the carry from the most significant bit of the addition, right? If I have an overflow, what do I do? In a normal machine, can you think of a solution that is safe to do? Again, I cannot have a 33-bit register. I cannot store that register. So add to another register, then you will be using another register for 1 bit, right? Yeah, you throw in an exception, simply used as a flag, right? You tell the user or you tell the machine that, well, there was an overflow. What to do with it, it's up to the user, right? You just know that there was something wrong, right? And in that case, you handle it. And in reality, these are things you can very easily try in your machine right now. Open any interpreter, compiler, MATLAB, Python, doesn't matter. Try to add the max n with the max n. And see what is the output you get, right? Your max n in your machine can be 32-bit or 64, depending on your machine. But if you add 2 into them and look into the results, see what's going to happen. Okay, I guess all of this is a bit of a detailed discussion that we can skip because it's specific to maps. Shift operations is a type of operation that we didn't discuss. But it's a bit of straightforward. Simply shift is that logic. It's one of the easiest, or I mean, easiest in terms of hardware operations to support. And for that reason, sometimes people trying to optimize even division, for example, of multiplication and shift operation, right? So for example, if I'm multiplying by 2, what does this represent? How can I represent using shift operation? Shift left by 1 bit, right? If I'm dividing by 2, shift right by 1, right? So simply shift operations, because if you think about them, they are just really putting the wires in different places, So you take the register value and you basically, instead of making bit 0, you start from bit 1. Then you either rotate or to sign extension, the things related to signed, unsigned that we discussed earlier. The shift operations are usually very, very easy to do. What is the format of this? Well, we already mentioned that the shift and all the logic operations is part of the R format of the arithmetic. So again, you have the opcodes, the functionality. And if you remember, part of this R format, we have what we call shift amount, right? We had two operands, one destination and the shift amount. This shift amount is used if you have a fixed constant value shift. Right? So here, for example, I'm saying I need to shift S0 register by 8 bits and put the results in T2. This is shift left and this shift right. So that the shift amount is only 5 bits. Why that's enough? Well, it's already written here, but maybe I should have asked you before. Simply, my registers are 32 bits, right? So you have 32 bits that you want to shift. If you have 5 bits and you use them as the exponent of the shift amount because you are shifting by 2 to the power, right? In that case, 5 bits are enough to really shift the whole 32 bits. If I'm saying, for example, 8 here, so the constant is 8. What would be the value of the shift amount? It would be 3, right? 1, 1, 3 zeros. Why that's the case? Because I'm taking the shift amount and making it 2 to the power. So if it's basically 3, I'm going to shift by 2 to the power 3, which means 8. Right? See that the point? So here's 5 bits shift amount is enough to shift 32 bits. The value is simply to the power 5, 31 position. Okay, so we call these operations logical shifts, right? I don't know if you already discussed this in the digital design course, but there is a problem with the logical shifts. Logical shifts don't care about signed and unsigned. They don't have this sign knowledge. They only embed with zeros, right? So if you're shifting to the right, you add a 0 to the right. If you're shifting to you're shifting to the left, you're adding a 0 to the right. If you're shifting to the right, you're adding 0 to the left. But what if you have a signed number, especially if you are shifting right, because you are changing the sign, or shifting also left, you're throwing out the sign. In that case, you need to make sure you keep your sign intact, right? So this must go through an example and then we will stop. So assume I have a value like this, and I'm talking only about a 4-bit value right now. If I'm telling you that this is unsigned number, what would be the value of that? 8, right? But if I'm telling you that this is signed, what would be the value? -8, okay. -7, right? Okay. So let's say this is -7. In fact, the absolute value doesn't really matter for our discussion right now, but the point is, if this was unsigned value, if I want to shift to the left, right, by 1 bit, what is going to happen? What do you think? Well, simply it will be 0, 0, 0, and then I'm adding a 0 here, and the 1 will be shifted here, right? So, well, you'll end up with this stuff, right? So it's 0 in your 4 bits. Simply the 8 becomes 16, right? But it depends on whether you are supporting 5 bits or not, right? But if this was an assigned value and you are shifting, so simply this was 8 value, it became 16. But if you look into this thing, it still remains all zeros because you had an overflow. But if you are shifting assigned value, the same exact value 1, 0, 0, 0, then you are shifting it to the left by 1 bit. You turn it a negative number into a positive number, right? So you cannot, in fact, it's not only an overflow, but you also have an incorrect value, right? Think about if you do the other way around. This 8 you want to divide by 2, so you want to shift to the right. What is going to happen? You're embedding a 0 here, right? So this becomes 4, which is in fact correct, right? But if this was the same value and became -7, if you are shifting to the right, what would be that value? It's 4 as well, which is wrong if this was a signed number, right? Because you lost the sign, it turns out to be positive. If you divide a negative number by 2, it doesn't become positive, right? It has to remain negative, right? How to keep it? Well, instead of embedding a 0 here, you embed the sign itself, right? Which is 1. So in the logical shift, you embed zeros, but they only work with signed values. While if you are dealing with signs, you need what we call arithmetic shifts, the SRA and the SLA instructions. Those ones handle the sign bit visually. So they make sure that if you are overwriting the most significant bit, they keep it and then simply replace the zeros with it, right? Make sense? So the summary is, for the arithmetic shifts, you keep the sign because you don't want to change the sign of the value. Shift is not supposed to change the sign because the shift is either a multiplication or division. If you are dividing by 2 or multiplying by 2, arithmetically, the sign should remain the same, right? A negative number by 2 or a negative number by 2, well, divided by 2 or multiplied by 2 should really remain negative. It cannot be positive, right? You cannot use logical shifts with the negative numbers. That's why we use the arithmetic shifts. Good. So let's stop here. By this, we are done with in fact, the ISA topic. Next time, we're discussing the data path and the control path.